Hello and welcome to another episode of How to Understand X. Today we're going to be tackling implicit differentiation. Now, we did talk about this in our previous derivatives video, but I feel like I didn't give it as much as I would have liked to, and I'm going to be doing a bunch of practice problems in implicit differentiation to make sure that everybody understands it, at least relatively well. I don't know how many I'm going to do, but I'll just find something on the internet and we'll work through it. But before we get into implicit differentiation, we need to talk about the chain rule. Now, the chain rule is as follows. If y is equal to f of g of x, then y prime is going to be f prime g of x times g prime x. Now, what does this mean? Well, if f is a function that uses another function as input, then you differentiate f normally, and then you multiply it by the derivative of the input. And we'll talk about that in a little bit, but let's first do a small proof of the chain rule. This is going to be relatively quick. I feel like this isn't super necessary to know, but it is nice. So, yes, if limit as h approaches 0 of f of x plus h minus f of x all over h is equal to f prime x, then we can use g of x as our input and then plug in g of x for every spot where g of x exists. So the limit as h approaches 0 of f of g of x plus h minus f of g of x all over h. And now we're going to multiply this by g of x plus h minus g of x all over g of x plus h minus g of x. You might be wondering why we did this. It's not so that we can cancel out this g of x plus h with that g of x plus h and this g of x with that g of x, but so that we can take this h out and then convert this g of x plus h minus g of x into a form that we've seen before. Now, just as like how fraction multiplication works, you need to have multiplication between the numerator and the denominator. So we can actually swap both the denominators to have g of x plus h go underneath this and the h go underneath that. Without using all these expressions, you might have, like, I think it's relatively intuitive to say that 1/2 times 3/4 is equal to 1/4 times 3/2, because you're still multiplying those two denominators, they're just in different places. Even though the expressions themselves have changed, the actual outcome hasn't. So we're going to have the limit as h approaches 0 of f of g of x plus h minus f of g of x all over g of x plus h minus g of x times the limit, getting a little bit ahead of myself, g of x plus h minus g of x all over h. And already this is looking very similar to what we have at the top of the screen, and that is the derivative, the limit definition of the derivative. So when we have a limit, we can actually split that limit between two of its factors. So in this case, the limit as h approaches 0 of all of this is equal to the limit as h approaches 0 of both of those individual terms. And then this is just going to be g prime x by the same formula that we have up there. And now we want, let me rewrite this a little bit higher. We want this function, the limit as h approaches 0 of f of g of x plus h minus f of g of x all over g of x plus h minus g of x, minus g of x to look more like this, right? And one way to do that is that we can see that in our top we have one single variable as our denominator. And if we wanted to do the same thing here, let's come up with a variable. We'll call it k, and we'll say that k equals g of x plus h minus g of x. Now that we've introduced a different variable k, we also need to change our limit. Instead of h approaching 0, it has to be k approaching something. So let's directly substitute h for 0, and then we would have g of x plus 0, which is g of x, and then g of x plus 0, which is g of x minus g of x, is going to be 0. Anything minus itself is 0, so k will be approaching 0 if h is approaching 0. And then from here, we want this to be split. Like, let's say if g of x plus h was something different, like g of x plus something, then it would look more similar to that. So, because, in this case, x is our input, but in this case, g of x is our input, so we want to have two things in there. And so if we try and solve for g of x plus h, let's just bring this g of x to the other side, or add it to the other side, and we would have g of x plus k. Alright. And then from here, let's just plug everything in. As h approaches 0, k is approaching 0, so let's write that down. And then this will be f of g of x plus h, which again we said is g of x plus k, minus f of g of x all over k. And now this is looking a lot more similar to our original definition of the derivative. Instead of h, we do have k, but in our denominator we have just our limit, which is, not our limit, the variable that is approaching 0, so that's going to be k, and that was h for our original. And instead of x, we are going to have g of x as our input, so this will be f prime g of x. And again, this is going to be multiplied by g prime x, because we did have that g of x plus h minus g of x in the numerator, and then we brought the h to the other side. So yeah, we did go through that a little bit quickly, but I don't think you need to know any of that. That's just kind of interesting, I guess, in my opinion. So we have f prime g of x times g prime x is going to be the derivative of f of g of x. And now we're actually going to use ddx notation for most of our implicit differentiation. So let's write down our y equals f prime g of x. And we could do this as, d dx and then do some stuff, but I kind of don't want to do that, so we're actually going to make, this isn't f prime g of x, that's just regular f of g of x. So I'm actually going to change this to be y of u of x. I know it's kind of unnecessary, but we are going to use a very different notation. So this is still a function of y, right? This is y of something that uses an input. So we are going to be finding the derivative of y with respect to x. And again, we said that this is f prime g of x. So this is going to be the derivative of y with respect to its input. So if this is the derivative of f with respect to its input, that's df dg. So this is going to be dy du, right? This is the derivative of y with respect to its input. I know I just did some truly awful circles, but I think you get the idea. Dy du is going to be similar to y prime u of x, which is the same notation that we had right there. So from here, let's Probably should just erase. From here we have u prime x, which looks a lot more similar. We have the derivative of u with respect to x is equal to u prime x. So if we were to write dy dx, that's going to just be the derivative of y with respect to u times the derivative of u with respect to x. And u is going to be our input function. And we actually sometimes don't need this middleman of u, which we are about to see. We are going to do, most of the time in implicit differentiation, we're going to differentiate y with respect to x, and y will not be explicitly defined as a function of x. So it'll look kind of like we are doing d dx of some function of y. And now this is going to be the same thing as this. Not exactly, but this will be d dx of y, and we will write this as the derivative of y with respect to y times dy dx. So this is just the derivative of this outside function, which in this case is going to be y. And you might even like to look at this kind of as dx of y of x, so that it's a little bit easier to see. We're doing the derivative. This is going to look like chain rule because x is some function of x. You might think of it as f of x in your head, but this isn't just x. This is some function of x, and then we're going to just be doing the derivative of y of x with respect to y. Y of x, and then that will be multiplied by dy dx. You can kind of think of it like the dy's are canceling, so that this d dx is the same, but that's not exactly what's happening. Maybe it's just a good way to remember it. But yeah, I might have made that a little bit more complicated than it needed to be, but this is a very important idea for implicit differentiation. You're not going to be differentiating functions of x. You're going to be differentiating functions of y, which we are going to implicitly define as a function of x. So we're going to be doing d dx of function of y, which we will define as a function of x. And that's just going to be differentiating with respect to y times dy dx. Again, the dy's aren't exactly canceling out. That might be a good way to remember it, but you are just going to be doing the derivative of y with respect to y times dy dx, which when we are implicitly differentiating, it's what we're going to most likely be solving for. So let's get into some examples. I simply searched up implicit differentiation practice on Google, and okay, yeah, this is an interesting first problem, but I think we have the capacity to work to it. Actually, this might be just a touch too complex. Let's go to a more normal function, and let's do the unit circle. That is x squared plus y squared equals 1. And so yeah, with this equation for the unit circle, if say this is an xy plane, then x squared plus y squared, let's say that's 1, 0, negative 1, 0, 0, 1, 0, negative 1, then that would be the unit circle. I know I'm not great at drawing circles, but sure, this is how it would look. And we are going to try and find dy dx, which, like in all derivatives, it's supposed to find the slope of some tangent line, and that's the tangent line to any point. For example, the square root of 1/2 and the square root of 1/2 is a point, and that would be, root 2 over 2, root 2 over 2, somewhere around there. We should be able to plug that point in to find a nice tangent line at that point. Something that might look, like kind of like that if it was actually on the circle. So, yep, that would be, a tangent line. And in order to do that, we have to find the derivative. And we could attempt to define y as a function of x. We can subtract x squared from both sides. We would have y squared equals 1 minus x squared. And then we can square root both sides, and we would get y equals plus or minus square root of 1 minus x squared, which isn't differentiable. Well, you can split it into two functions. You can split it into y plus square root of 1 minus x squared and y equals negative 1 minus square root of 1 minus x squared. But there's a much simpler and a more accurate way of doing this. And you can't really do that because y isn't a function. A function needs to pass the vertical line test. If you were to draw a line, it can only intersect at one point for it to be a function. And that's like one of the many different things that classify a function, but just in general, a circle cannot be a function. So for this, we can't define y as a function of x because x squared plus y squared equals 1 is not a function. We're going to have to find dy dx using implicit differentiation. Now, in order to do this, we're going to have to do the derivative of both sides. Differentiation is an operation, so any operation that you do, well, it's not 1 ddx, it's going to be ddx1, but any operation that you have to do to both sides. And then from here, we know that from our sum rule, the derivative of u plus v prime is equal to u prime plus v prime. So for this, it's just going to be the derivative of x squared with respect to x plus the derivative with respect to x of y squared equals the derivative with respect to 1, which, as I think we know, the derivative of a constant is going to be 0. Imagine this is y equals 1. I'm not going to draw the full xy plane, but if this is y equals 1, then the slope at any point, if you were to draw a line, the slope of these lines will always be 0. So yes, this will equal 0. And now the derivative of x squared with respect to x squared is a function of x. We can differentiate this normally. We use power rule, or n times x to the n minus 1, so we bring n, which in this case is going to be 2, times x to the 2 minus 1, plus d dx y squared. We're not going to touch that just yet, equals 0, and so we have 2x plus d dx of y squared, or the derivative of y squared with respect to x. And now from here, we can use our chain rule. We know that y squared is not a function of x, but we can differentiate y with respect to y. So d dy of y squared times dy dx. This is the same as the derivative with respect to x of x squared. Again, if y squared was a function, you might even think of it as y of x squared. We are going to be doing the derivative of the outside, or y prime x, times x prime. So, again, x prime is not, 1, because this x is just an idea. Y will be implicitly defined as a function of x, so x is going to be a function of x. It's not x the variable, it's just x the idea. So y prime x is going to be the derivative with respect to y. You are differentiating with y, so y prime x. And then x again is a function, so we are going to be differentiating with respect to x. So dy dx. Again, you could think of it like that, but yeah, if y of x helps you understand a little bit better, that's obviously great. But that's why we have to have this dy dx out here when we are differentiating this. Because we are differentiating this function of y, which we haven't explicitly defined as a function of x, but we are going to differentiate with respect to y so that we can multiply that derivative with respect to x. So from here, the derivative of y will follow the same way. We would have 2, which is going to be our n, times y to the 2 minus 1 times dy dx. So we would have 2 minus 1 is 1, so we'd have 2y dy dx. Alright, and then again we had 2x out here, and then we had 0 over here, and now we simply solve for dy dx. We have to bring that negative, or that regular 2x to the other side to make it negative, so we'd have 2y dy dx equals negative 2x, and then we simply divide both sides by 2y. And now we are left with dy dx is equal to negative x over y. And yeah, let's plug in our original point. We were talking about square root of 1 half, square root of 1 half, because if our function, or our relation, that's a more accurate way, it's not a function, x squared plus y squared equals 1. If we plug in square root of 1 half, square root of 1 half into that relation, we would have square root of 1 half squared, which is 1 half, and then square root of 1 half squared, which is also 1 half, then 1 half plus 1, 1 half plus 1 half equals 1. And then from there, let's plug in this point, and we would get there. Now, you might have heard about how this corresponds to x equals, well, even then, you don't need to know too much trigonometry, but cosine corresponds to x, and then sine corresponds to y, not sine of y, even though we will talk about that in a little bit, I imagine, but sine y. And then from there, sine of x were to equal root 2 over 2, that would be x equals pi over 4. So if we were to drop a line, this angle is going to be pi over 4. So the tangent line at that point is going to be negative root 1 over 2 over root 1 over 2, which is going to be negative 1. And, if we just look at this graph and pretend it was a good one, we could say that the slope of a tangent line at that point is going to be negative 1. So yeah, I hope that kind of gives an idea of what we're going to be doing, but if it doesn't, don't worry, we have a bunch of examples to work through. So now let's go to our weirdly difficult first one, and that is ax squared plus 2hxy plus by squared plus 2gx plus 2fy plus c equals 0. And obviously there is a lot, but we're going to have to do kind of what we did for our first problem. With x squared plus y squared equals 1, we didn't have too much, so we were able to differentiate both sides like this and do ddx of all of this. But a more efficient way of handling this would be to simply take all of the y's, it's not all of that, all of the terms that have y in them, and then every term that has x, and then do some nice separation. So we want everything with a y on one side and everything with the x on the other side. In this case, we do have a term that has both x and y, It's not really personal preference. I think it's a lot easier if you just have every term with a y on the other side, but I think there might be a way to have 2hxy on the other side when you differentiate, even though you'll have a lot more work to do. But yes, let's just put every term that has a y on one side, so 2hxy plus by squared plus 2fy. And then from here we can bring our ax squared to the other side, make that negative ax squared, and then minus 2gx, and then minus c. And now we're just going to differentiate with respect to x for both sides. We are trying to find the derivative with respect to x. Again, d dx should be over there, but I'm just writing this out right now. And we're going to use quite a few interesting rules. I'm actually going to do this side first, the right side, because I think it's a little bit easier to see. All these fancy variables are tricks. You don't actually need to do anything with these a's and g's and c's and d's. You only need to understand that these are constants. Say a equals 3. If we had negative 3x squared, then if we were to do that derivative, we can simply bring that 2 out to the front. We'd have 2 times negative 3 times x to the 2 minus 1, which is going to be negative 6x. And if you remember, if a is still equal to 3, then negative 6x divided by 3 is equal to negative 2x. So, yeah, negative ax squared is still going to be negative 2x. If you just bring that 3 back over there. So, a is a constant. It's not, whoops, a is a constant. It's not going to change anything. So, when we differentiate, we're not going to actually care too much about these a's and b's and c's. It's only going to be the x's and the y's that are important. So, let's do this derivative. I kind of already did it, but we bring that 2 out to the front. We'd have 2 times negative a x to the 2 minus 1. 2 minus 1 is 1, so we'd have negative 2ax. I am going to do most of these without showing every step. I'm hoping that the, n to the x should be ingrained in my head. I was about to say n times x to the n minus 1 is relatively ingrained in our heads, but, doesn't hurt to think about it. We'd have negative 2ax, and then negative 2gx. This is x to the 1, so 1 minus 1 is 0. And if you bring that 1 out, it's still going to be 1, so negative 2g. And then the derivative of a constant is going to be 0. Again, c is not a variable, it's just a constant. So this would be 0. I'm not going to write 0. But now we have to do the more interesting part, and that's d dx of all of these functions. So let's write them out. d dx of 2hxy plus d dx by squared plus d dx f2fy. Now, I'm going to erase this. If you want to follow along, then you can write this down if you'd like, but I think it's also beneficial to just kind of watch. So now we're going to have to implicitly differentiate and use product rule at the same time. Now again, 2h is a constant. If h equals 4, then we'd have 4xy. It's not 4xy, it's 8xy, because 4 times 2 is 8. But we'd have 8xy, and then this is just a normal constant, so you can pull that out and then do xy prime. So 2h doesn't actually impact any of the differentiation that we're going to do. So when we do dx of 2hxy, just ignore the 2hxy for now. And when we're doing product rule, we're going to have to do our first term, which in this case is going to be, let's say 2hx, and then our second term is going to be y. So let's do that. We'd have the derivative of, well, actually, since it is a constant, let's just make this simple, and we'd say that 2hxy, this derivative is the same as 2h times the derivative of xy. Again, 2h is a constant, so it doesn't get differentiated to 0, so we can just pull it out. So when we're doing the derivative of xy, y is not explicitly defined as a function of x, so we're going to have to use product rule. We're going to have to do u v prime is equal to u prime v plus u v prime, and we're going to have to do the derivative of the first, which is x prime, times y plus x y prime. All right, and again, we said that y in this case is going to be dy dx. It's not actual y, but we're getting a little bit ahead of ourselves right now. So let's write this out. We have 2h times x prime, which is going to be 1 times y plus x times y prime. All right, and now we have some interesting stuff going on. This 1 times y is going to evaluate to y, and y prime we're going to have to differentiate with respect to y, so d dy of y times dy dx. We're trying to do the derivative with respect to x of y, so we're going to have to use a chain rule to implicitly differentiate right there, and we'd have y plus x times y prime. So if we were to do the derivative with respect to y of y, we would just get 1, and then times dy dx. So we'd have x dy dx, and again, don't forget we did have that constant 2h hold out over there. All right, and now from there, let's distribute that 2h so we don't forget, and we would have hold on 1 second. We'd have two hy over here plus 2hx dy dx. Okay, great, and now we're going to do a slightly more easy derivative. It's just going to be by squared. Again, we're going to have to use chain rule. Y is not explicitly defined as a function of x, so d dx of by squared. B is a constant, so we're going to pull it out right now. B times d dx of y squared, and this one's a nice and simple n times x to the n minus 1, so 2 minus 1 is 1, and we would have 2 out in the front, so b times 2 out in the front, y to the 2 minus 1, so y, times dy dx. Again, that's going to be d dy of y squared times dy dx. This is equal to d dx of y squared. We're just using chain rule. That's what implicit differentiation is. So I'm hoping that you can see those connections and it's not, too complicated, but we are going to do a bunch of these. So 2by dy dx over here. All right, and then 2fy is going to be nice and simple. We'll bring that that 2f out in the front. So 2f out here times d dx of y, which is going to be d dy of y, which is 1, times dy dx. Again, that's going to be d dy of y times dy dx is equal to that. All right, so we have 2f dy dx. Remember, we did have that 2f that we brought out at the front, so this is going to be plus 2f dy dx. And now I think you might be able to see something that we can do. We can bring this 2hy to this other side. We'd have 2hy over here minus 2hy over there. And so we would have 2hx. The reason why we're doing this is to have all of our terms with dy dx on one side and all of our terms without dy dx on the other side, so that we can eventually factor and divide out. So plus 2by dy dx plus 2f dy dx equals negative 2ax minus 2g minus 2hy. And then from here we can factor out this dy dx. That's a thing that's common to all of these. Dy dx, 2hx plus 2by plus 2f equals negative 2ax minus 2g minus 2hy. And already I've said 2 quite a few times, so I think since every single one of these terms has a 2 attached to it, you can factor that out. So we'd have dy dx. I'm going to divide both sides by this, so we'd have dy dx is equal to negative 2ax, or yeah, negative 2ax, negative 2g minus 2hy all over 2hx plus 2by plus 2f. And again, each of these terms has a 2 in it, so we're going to factor out that 2. And we can also factor out this negative, because there's 3 of them. We'd have negative in the middle, or in the front, negative 2ax. I'm going to arrange it in the way that this answer is written on this Google question, plus hy plus g. So I guess you can arrange it in terms of like descending order, even though, x and y, it's not by degree, it's more like alphabet, but plus all over 2 times hx plus by plus f. And now we can cancel out those 2's, and we just have negative ax plus hy. I think we could fit that. It's kind of small. Negative ax plus hy plus g over hx plus by plus f. So yeah, kind of a crazy first example. I hope that was relatively, I wouldn't say easy, but I hope that made sense. It was a lot of implicit differentiation, and we did have to use product rule, but I think it was relatively normal. We just used that n times x to the n minus 1. And now let's pull up this next one. Okay, they're just not giving us any easy stuff. We are going to have we have x to the y is equal to e to the x minus y. Already, this is kind of a crazy function. This is kind of insane. First, the thing that immediately catches my eye is that we can do ln to both sides to get this e out of here. We'd have ln xy equals x minus y. Actually, hold on. I think, okay, I'm lying. I don't want to do this question. This is going to use generalized power rule, and I don't think we're ready for that yet. Yeah, I don't know. I think, actually no, let's not do that one. Let's do something a little bit easier. If anybody wants to know how to do that, then, in another video we can do that. But I want to start off with some more normal ones. And we're going to have x sine y equals 3 sine y plus 4 cosine y. And we're trying to find dy dx. Alright, this is a slightly more normal one. It's definitely also kind of tricky, but I think we can do it. Now, already, I see that we have a bunch of terms with y in them, so it's not really simple to take away the x. We know that there's only one x in this situation, so it's kind of hard to isolate it. So I'm going to try by bringing this to the other side and then factoring out that sine y. So we have x sine y minus 3 sine y is equal to 4 cosine y. And now from here we can take out our sine y. We can say that sine y is a common factor, so we'd have sine y times x minus 3 equals 4 cosine y. And now we'll simply divide by sine y on both sides. And now you could write this as cotan y, but, why would we do that, right? I mean, maybe if you know the, things off the top of your head, that might be helpful, but might as well just kind of, do this. So we have x minus 3 equals, well, actually, let's put our 4 cosine y over sine y on this side, and then let's have our x minus 3 on this side. Okay, so this is going to be another relatively interesting one. With this one, I think we obviously are going to have to use our quotient rule, which, to remind it, it's going to be u over v prime is equal to u prime v minus u v prime all over v squared, or you might have heard it as top prime bottom minus top bottom prime over bottom squared, or, there's a bunch of ways to memorize it, but I like this UV notation. I feel like it simplifies it rather nicely. So in this case, we're going to be doing d dx of 4 cosine y over sine y. So we're just going to bring that 4 out there. It is a constant, so it's not going to affect our derivative. 4 times d dx, because we have to do this d dx to both sides. And now this is just going to be the same as 4 times d dy of cosine y over sine y times dy dx, which is, again, what we are going to try and solve for. And from here, we just use quotient rule. We have to do the top prime, which in this case is cosine y prime. Let's write it like that, times sine y minus cosine y over sine y prime all over sine y squared. Now, from here, we can write this as sine y, because the derivative of negative sine y times sine y minus cosine y cosine y. So the derivative of cosine is negative sine, and the derivative of cosine is derivative of sine is cosine, and then the derivative of cosine is negative sine. So yeah, those were good to remember. And from here, negative sine times sine is going to be negative sine squared. Negative cosine times cosine is going to be positive cosine. So negative sine squared minus cosine squared, y, I don't know why I said positive cosine squared, all over sine squared y. And now from here, you might be able to see that we can factor out a negative on that numerator. We can say that since both of these have negative in common, we'd have negative pulled out in front, negative sine squared y plus cosine squared y all over sine squared y. And for all of our trig friends, we know that we can simply say that sine squared plus cosine squared is equal 1. So we have 1 over sine squared y. And you could just memorize that cotan x, that derivative is equal to negative cosecant squared. So 1 over sine is cosecant, which is, maybe important. I think it's, beneficial. Maybe it's a little bit of a time waste, but it's beneficial to do quotient rule and product rule and get those fundamentals down as much as you can. So we have negative 1 over sine squared y times 4. So we're just going to bring that 4 up here. And now from there, we have this multiplied by dy dx. And yeah, that's going to be what's on the left-hand side of this equation. But, so negative 4 over sine squared y. But we also did have another side of this equation. Well, it's times dy dx. So we have also d dx, because again we have to do it to both sides of x minus 3. And this is going to be a nice and simple x prime, which is going to be 1, minus the derivative of a constant, which is going to be 0. So we're going to have this is equal to 1. And now for something like this, when you have a fraction like this and you're going to divide by a fraction, if you're doing 1 over that fraction, you simply flip this fraction. So let me just do that. Let's even do normal numbers. We have 3/4. Let's not do. Let's do 1 divided by 3/4. For this one, we have to flip this thing, and we'd have 1 times 4 over 3. So we change this thing to division, and then we flip the fraction. So the 1 over negative 4 over sine squared y is going to be equal to, so dy dx is going to be equal to these flipped. So it's going to be negative sine squared y over 4. Which, simplified rather nicely. Hoping that's relatively normal. Now let's do something called a differential equation. I know that might sound a little bit weird, but I think it's okay. Let's do this. So now we're going to have y is a function of x. We're not going to define it explicitly, but we are going to say that y is a function of x, and then ln of x plus y is equal, minus 2xy is equal to 0. And again, we can't really isolate, and they say that y prime 0 is equal to something. So we are going to try and find dy dx, and then plug in some value of 0 to find y prime 0, which is what they want. And then from here, it's going to be kind of a weird one. It's nothing impossible, of course, but we're going to have to do some ln differentiation. So, this one's going to be maybe a little bit ugly. I'm not sure if I'm going to solve this in the best way possible, but let's first plug in y of 0. Now, y prime 0, if we have a dy dx, I'm going to assume that it's going to have to be some amalgamation of x's and y's in the numerator and denominator of something. So we need to have both x values and y values to plug in as an ordered pair, so that we can actually, solve for dy dx. So let's do that. We are given that x equals 0 for this specific equation. So if x equals 0, you'd have 0 plus y minus 2 times 0 y equals 0. Now we have ln of 0 plus y minus 0 equals 0. We have ln of y is going to equal 0. All right, and then from here, we have, well, somewhat interesting equation. You might have seen it before, but ln of anything, if that anything has to equal 0, then ln of 1 is equal to 0. And in order to cancel out ln, we have to use its inverse operation. So let's put e to the power on both sides, and then from here we can get a nice 1. So e and ln cancel out here, we'd have just y, and then e to the power of 0 is going to be 1. So our point that we are going to plug in to our dy dx is going to be 0, 1. Alright, and then from here, we're going to have quite the derivative. So since we have terms with y on both of our terms, we're not going to actually be able to split anything. We're just going to do our derivatives. And ln of u is equal to u prime over u. I did a proof for this a little while ago, but, you know, if that interests you, if you want to know why that's true, then you can watch that video. But we have u prime, which in this case is going to be x plus y, that derivative, which we're going to do dx of, by the way, all over x plus y. Alright, so yes, if u in this case is x plus y, then we are going to have u prime up top and then u in the denominator, and then this is going to be a nice product where we're going to have 2 times xy prime. So again, uv prime, it's going to be u prime v plus uv prime, and then we're going to have minus 2 times u prime, or not u prime, it's going to be x prime in this case, x prime y plus xy prime, and that's equal to 0. And now from here, we just have a bunch of derivatives to evaluate, and now ddx of x is going to be 1 plus ddx of y, which again, it's going to be dy of y times dy dx, all over x plus y, which dy of y is going to be 1 times dy dx, so we're going to have 1 plus dy dx on the numerator, and then x plus y in the denominator. And then from here, we can do x prime, which is going to be 1. So let's keep that in the back of our mind, 1 plus dy dx over x plus y. And then we can do the derivative of x, which is going to be 1, so we have minus 2 times 1 times y, plus x times y prime, which is again dy of y times dy dx. This evaluates to 1, so we're just going to be left with x times dy dx. I know that's not the greatest x. Let me write that. But yeah, this is kind of not going to be the greatest to solve for dy dx for, but we're going to try our best. And let's write it all out now. We have 1 plus dy dx in our numerator all over x plus y minus 2, I'm just going to distribute that minus 2 to both of these, minus 2y minus 2x dy dx. And now we need to isolate this dy dx, which isn't going to be easy. First thing that comes to mind is we're going to have to split this fraction into 1 over x plus y plus, I don't know why I wrote that fraction so large, plus dy dx all over 1 plus x plus y as well. if if dy dx was a simple number, then that would be a normal way to split this addition. And now from here we can simply factor out that dy dx from the numerator, and we're just going to be left with 1 over x plus y. So let's put down our ideas. We have 1 over x plus y plus dy dx, which we factored out of the numerator, times 1 over x plus y minus 2y minus 2x dy dx, which again we just distributed at -2 for. That's going to be equal to 0. And then from here, because derivative of 0 is going to be 0, again, if this was y equals 0, you pick any point, the slope of a tangent line is still going to be 0. So from here, we're going to do some fancy factoring. We have dy dx in both of these terms. We're going to have dy dx out here, 1 over x plus y minus 2x, and then we're going to bring our -2y to that side, and then our 1 over x plus y to the other side as well. We're going to have 2y plus, not plus, minus 1 over x plus y on this right hand, and then we're simply going to divide by 1 over x plus y minus 2x. So, yeah, let's write that down. We have dy dx of 1 of x plus y minus 2x all over, not all over anything, is equal to 2y minus 1 over x plus y. So we're simply going to divide by 1 over, I don't know why I'm writing these fraction bars so large, 1 over x plus y minus 2x divided by 1 over x plus y minus 2x. And then from here, I know my handwriting kind of deteriorated right there, but it's going to be 1 over x plus y. And again, remember, our point for this one was 0, 1. Our x was equal to 0 and our y was equal to 1. So we're going to plug in 0 and 1 for all of these. We're going to have, let me erase this. We have dy dx is equal to all of that. And now let's plug in our y's and zeros. Our y's and x's. And we have 2 times 1 minus 1 over 0 plus 1 all over 1 over 0 plus 1 minus 2 times 0. Now this is just going to be simple math. We have 2 times 1, which is 2, minus 1 over 0 plus 1, which is 1, all over 1 over 0 plus 1, which is 1, minus 2 times 0, which is going to be 0. 2 minus 1 is 1, 1 minus 0 is 1, so we have 1 over 1, which is going to be a nice and simple 1, which, it feels like it kind of invalidated all of our hard work, but I think it's even more beautiful when really complicated ideas can look really simple. But yes, the solution to all of that, let's write down our original equation. We have ln of x plus y minus 2xy equals 0. And then the solution to dy dx when x is equal to 0 is going to equal positive 1. So yeah, this is called a differential equation because we are given a point and we have to find a specific solution to the derivative. So that's why it's called a differential equation. And from there, we can go on to our next example. Okay. Interesting looking. We have, well, honestly, this isn't too bad, I don't think. We have arctan of x squared plus y squared is equal to alpha. I think that's what it's called. And we are trying to find dy dx. Again, alpha is a Alpha is going to be just a constant, so it's not going to be thorn in our throat or anything. Is that the correct turn of phrase? I'm pretty sure it's not. No, it's thorn in somebody's side. Okay, whatever. So let's do this. I already see a bit of a complication. We are going to have to do the derivative of arctan, which, in case anybody's forgot, is the derivative of arctan of x is 1 over 1 plus x squared. Since we are given x squared plus y squared instead of x, we're going to have a lot harder of a time doing that. But, you know, it's fun, kind of. And, so first off, I see that we are going to have to do some kind of chain rule. So let's think of this as, well, I mean, you know, we were already going to use chain rule, but we're going to have to do it slightly differently now. So let me think. I think we should probably write this in U notation. I know we usually use U in terms of U sub, like for integration, but this is just going to help me think because I'm kind of doing this along with you. So let's say that x squared plus y squared is equal to some function u, and then we are going to try and find arctan u's derivative. So using chain rule, we're going to have to differentiate arctan times u prime. So like using that f prime g of x times u prime x, I mean not u prime, times g prime x. So derivative of the inside times derivative of the outside, we're going to have 1 over, let's write arctan out right here. And again, we said that this derivative of arctan x is going to be 1 over 1 plus x squared. So we're going to have 1 over 1 plus u squared times the derivative of what was on the inside, so u prime. And u prime we are going to differentiate with respect to x, so let's actually resubstitute our u back in. We're going to have d dx of x squared plus y squared. Okay, this isn't too bad, actually. I made that unnecessarily complicated. No, this is fine. I was just thinking of it kind of weirdly. This isn't too bad of a derivative, but let's put it together. We have d dx of x squared plus y squared. That's going to be in our numerator. It's going to make it slightly easier to solve, I think, towards the end of this. But d dx of x squared plus y squared is in our numerator because we just brought it up. And then we have u squared plus 1, which, again, I don't think I needed to do that, but it's going to be 1 over x squared plus y squared squared. So, kinda, it's gonna be a journey to solve for dy dx after all of this. But let's use our n times x to the n minus 1, and then the derivative of x squared is going to be, we bring that 2 out there. I don't know why I keep writing d dx equals x squared. It's just d dx x squared. But we bring that 2 out to the front, and then we have 2 times x to the 2 minus 1, which is 2x. And then same idea with y. Instead, we're going to have to differentiate with respect to y and then multiply by dy dx. So I won't say one last time because I'm going to write this over and over again until it's kind of like entrenched in your brain, but d dy of y squared times dy dx is the same as d dx of y squared. So from here, d dy of y squared, same idea as 2x, it's just going to be a nice and simple 2 x dy dx. So, not 2x dy dx, 2y dy dx. So we have 2x plus 2, let's put that down, 2y dy dx all over 1 plus x squared plus y squared squared. Okay. Okay, that's doable. That's doable. And again, we didn't have to be scared of this alpha. I think that's how you're supposed to refer to the symbol. This is a constant, and the derivative of a constant is 0. So all of that is going to equal 0. And now from here, it's going to be a journey to try and solve for dy dx in here. But, we can do it. Let's first use our algebra. We know that x plus y squared equals x squared plus 2xy plus y squared. So if we have x squared and y squared instead of x and y, it's going to be x to the power of 4, 1 times x to the power of 4 plus 2x squared y squared plus y to the power of 4 all under 2x plus 2y dy dx. That's going to be equal to 0. Actually, I'm not sure if that's the simplest way to solve this. Let me think for a second. So we are going to have to split this. Oh, no. No, I know how to do this. It doesn't need to be that hard. If we tried to do it that way, it would have been a lot more difficult. But there is a much simpler way to solve this, and it's going to be kind of a nice trick. We're going to split our fraction into two fractions. We're going to have 2x over 1 plus x squared plus y squared squared on one side. And then we split that, so we have 1 plus... yeah, if I was going to do it that way, this would be a much longer video. Plus 2y dy dx. I'm using the wrong thing. 2y dy dx over 1 plus x squared plus y squared squared. And that might seem like it didn't really do too much, but it's actually done quite a bit, because now we can simply isolate the thing that does not have dy dx by bringing it to the other side. And so we have a nice 2y dy dx. Actually, for the sake of clarity, dy dx is in the numerator, so we can bring it out to the front of our fraction. We have dy dx times 2y over 1 plus x squared plus y squared squared. Again, this is only possible because dy dx is in the numerator of our problem. And then this is equal to negative 2x over 1 plus x squared plus y squared squared. Again, it's going to be negative because we have to subtract it. And now from here, it's actually quite a nice little trick. We're going to simply divide by 2y over 1 plus x squared plus y squared squared. And this is going to simplify quite nicely. 1 plus x squared plus y squared squared. And now when you flip this, you're going to have to flip it because you're doing fraction division. When we flip it, we're going to have 2y in the denominator and 1 plus x squared plus y squared squared in the numerator when we flip that fraction, all over 2y. And now, since these are both the same term, let's actually cancel these out too. We have negative 2x over 2y. Both of those can be divided by 2, so we have dy dx equals negative x over y. I know it was quite the interesting journey, but, it's definitely It's definitely possible. And so, yep, dy dx is going to be negative x over y for arctan x squared plus y squared equals any constant. And now let's do some more practice problems. We have, okay, yeah, I'm gonna not do that one. That requires integration. That one's definitely not happening. That's a power series. Okay. Okay. Now I just went into like a super easy question, but I'm gonna take it. We have 4x squared minus y squared equals 9, and we're gonna find dy dx. I know in comparison to our last couple that seems ridiculously easy, but I swear I got like two very odd questions. One was like integration and differentiation. You had to like inverse those operations in order to get the correct answer, and then the other one was like an infinite series. So we're not going to get into any of those complications. We're just going to do this nice and simple dy dx right here. So we're going to have to do d dx of all of this. So differentiate with respect to both sides. We bring that 2 out in front times 4, so we have 8x to the 2 minus 1, which is 1. Didn't need to write that. So we have 8x minus 2y. So we're going to do dy of y squared times dy dx. So that's just going to be 2y. 2y dy dx. That's going to be equal to 0. Then from here, we simply bring that negative 8x to the other side. We have negative 2y dy dx is equal to negative 8x. And we get a nice and simple dy dx is equal to, let's divide by negative 2y on both sides. Cancel out the 8 and the 2 to get 4 on the numerator, and then the 2 negatives cancel out as well. We have a nice and simple positive 4x over y. Okay, yep, that's correct. And now let's go on to, oh, this one's interesting. We're going on to another nice, weird one. And, well, it's not super weird. It's relatively simple, actually, but, interesting thinking behind it. We have 1 over x plus 1 over y is equal to negative 1 over 12. Now, we're going to have to do d dx of all of it. So, again, you could bring the 1 over x to the other side and then do that kind of derivative. I'm just kind of flip-flopping because I can't keep my story straight and I don't know which one's easier. It's kind of on a case-by-case basis. Whatever you like, you do. I think, for the most part, it's probably easier to isolate the y's and almost always, not even always put your y's on the left side and always put your x's on the other side. And if you have a term that has both an x and a y, bring it to the left. So that's the correct way to differentiate, but I'm not feeling correct right now. So we're going to do derivative of x to the negative 1 plus the derivative of y to the negative 1 ddx. And again, derivative of a constant is going to be 0. From here, we bring that negative 1 out front. We have negative 1 times x to the negative 1 minus 1. So let's write it as negative x to the negative 2 plus, same thing, we bring that negative out front, negative y to the negative 1 minus 1, negative 2 times dy dx. We did dy of y to the negative 1, and then we have to multiply that by dy dx to get ddx of y to the negative 1, and that's going to equal 0. And then from here, we have negative 1 over x squared minus 1 over y squared times dy dx equals 0. And from here, we simply add the 1 over x squared to the other side. So negative 1 over y squared dy dx is equal to positive 1 over x squared. And we divide both by 1 over y squared, or negative 1 over y squared. You flip those fractions, and then this will just be multiplied to the numerator. So we're just going to have dy dx is equal to negative y squared over x squared. Alright? And yep, that's correct. Next one. Ooh, okay. This one's interesting. This one's kind of like what I think was our second example problem. It's going to be an interesting one. It's a equation. You are given a point and you're trying to find dy dx at that specific point. So our point is going to be 2x squared minus 3y squared is equal to 5xy. And then we are going to find dy dx at 2, negative 4. So they give us the y and they give us the x, so we don't have to solve for anything. So let's do this derivative. Well, this one I'm going to bring y's to one side and then x's to the other side. So this is a trick that I kind of like to do in my head. I know that this is a negative, and if I bring this 5xy to that side, it is also going to be a negative. So in my head, I actually bring this 3y squared to the other side, so it becomes 5xy plus 3y squared, and then I keep this 2x squared on the left-hand side. But since I said we should always keep our y's on the left hand and our x's on the right hand, we can just kind of flip this in our minds to 5xy plus 3y squared is equal to 2x squared. Alright, and now we will simply do d dx of all of this. And from here, it's product rule, like we've been doing. We can bring that 5 out there, so we'd have, well, we're doing d dx of 5xy first. So we'll bring that 5 out here. We'd have 5 times the derivative with respect to x of xy. And this is going to be x prime, which is 1 times y plus x times y prime, which is going to be 1 times dy dx. I'll write it one more time. But we have d dy of y times dy dx is the same as d dx of y. Alright? And then, again, d dy of y is going to be 1, so we have x dy dx. And then this is plus 3y squared, or the derivative with respect to 3y squared, or the derivative of 3y squared with respect to x. So we bring that to, it's not a constant, I'm not bringing it out there, but I'm bringing it out here. We'd have 2 times 3, which is 6, times y to the 2 minus 1, which is 1, times dy dx. Right, great, now we have y plus x dy dx. Well, we have that 5 in the front, so we have 5 times y plus x dy dx plus 6y dy dx equals 4x. Or, sorry, I didn't show the work for that one. We just bring that 2 out to the front. 2 times 2 is 4, times x to the 2 minus 1, which is 1. So we have all of that, and now let's distribute that 5. We have 5y plus 5x dy dx plus 6y dy dx equals 4x. All right, great. Now we bring that 5y to the other side. Does not have a dy dx attached. And just to do it in one step, we're going to factor out that dy dx as well. We'd have 5x plus 6y, only two terms with dy dx attached to it, equals 4x minus 5y. And then let's plug everything in. We have dy dx is equal to 4x minus 5y all over 5x plus 6y. So let's plug in our 2's and negative 4's. We have 4 times 2 minus 5 times negative 4 over 5 times 2 plus 6 times negative 4, right? And then this is 10, negative 24. This is 8, negative 20. So we have 8 minus 20, which is negative 12, over 10 minus 24, which is negative 14. Both of these are even numbers, so we can divide both by 2. 12 divided by 2 is 6. 14 divided by 2 is 7. And then negatives cancel out. We have positive 6 over 7. Wait, did I do something wrong? Okay. So 6 over 7 was an answer, but it's not the correct answer, which means I've definitely done something wrong. Let me do this out for a second. Okay. Oh, I was doing it in my head, and yeah, no. When you bring that 2x squared to the other side, I'm not going to cut this out, mostly because I don't know how to cut this out. But it's important to know that everybody makes mistakes. We bring that 2x squared to the other side, and that becomes a negative 2x squared. So we have 2x squared minus 3y squared. I guess this is why you should never do shortcuts, but we bring this to the other side. And then we have, wait. No, okay. Let's write it the correct way. We have 3y squared, 2x squared over here, and then equals 5xy. So we bring that over here. Wait. Now actually I don't know what I did wrong. Hold on. Let's think. Okay. Well, I'm doing it out now. Doing it by hand, and I didn't actually bring the y's to the other side and then bring the x's to the other side. It's not a problem with the differentiation, it's a problem with the signs. So I'm actually going to not bring anything anywhere. And when we do 2x squared, that derivative, it's going to be 4x, like we said. 3y squared, that derivative is going to be 6y dy dx. And then the derivative of 5xy is going to be 5y plus 5x dy dx. And yeah, I didn't show any work for those ones because those were all the ideas that we agreed upon. But from here, I don't. Okay, so oh, wait, no, never mind. Okay, I took a weirdly long amount of time to not pay attention to my work. I'm sorry about that, but it was actually a much simpler problem, much simpler mistake. When you do minus 5 times minus 4, that's going to be plus 20. So we have 28 over negative 14, which is going to be negative 2. Yeah, I don't know how I missed that. I did waste like 5 minutes just thinking what I did wrong, even though my mistake was clearly in front of me. But on that sad note, we're going to go and do another nice practice problem. Okay, this one's not, more difficult than the last, but it's just the same, same old, same old. But practice is practice. Let's do this one, which is x to the power of 6 plus y to the power of 6 plus 6x squared y squared minus 8 equals 0. Now, this is the same. Oh, and our point that we are going to plug into dy dx is 1, 1. Okay, so from here we're going to have to differentiate from both sides with respect to x. So let's do x to the power of 6 first. We bring that 6 to the front, and then we have 6 minus 1, so 5. So we have 6 times x to the 6 minus 1 plus the derivative with respect to x of y to the power of 6, which again, we bring that 6 out front, and then we have 6 minus 1, so we have 6y to the 6 minus 1, which we said was 5, times dy dx. Again, what we did is d dy of y to the power of 6 times dy dx. That's what that operation is. And now from here, we have 6x to the power of 5 plus 6 y to the power of 5 dy dx. Then we have a nice product rule to do. We bring out this 6 because it is a constant, so we have 6 times plus 6 times d dx of x squared y squared, and then this is going to be product rule, so we have to do derivative of the first times the second, so we bring that 2 out front. 2 minus 1 is 1, so we have 2x y squared, and then plus, we're going to have to do first times derivative of the second, so we said that if we bring that 2 out front, then do 2 minus 1, we're going to have 2y, so times 2y, and then this is also going to be multiplied by dy dx because y is not defined as a function of x. And then from here, let's distribute our 6 to all of our terms, then simplify slightly. We're going to have plus 12x y squared plus 12x squared y dy dx. And then again, derivative of a constant 0, so derivative of 8 is going to be 0, and derivative of 0 is going to be 0. And now let's bring our like x squared and y squared and all that stuff to one side. So we have 6y to the power of 5 dy. Well, actually, going to do this in one step. We have dy dx common to both of these terms, so we're going to bring them out. Dy dx of 6y to the power of 5 plus 12x squared y, and that's going to be equal to negative 6x to the power of 5 minus 12x squared y. And now this is all going to be divided. So we're going to divide both by 6y to the power of 5 plus 12x squared y. 6y to the power of 5 plus 12x squared y. And now we simply plug in 1, 1 into that point. So let's do that. We have negative 6 times 1 to the power of 5 minus 12, 1 squared, 1 all over 6 times 1 to the power of 5 plus 12, 1 squared, 1, and then negative 6 minus 12. I'm just going to ignore the 1's because anything times 1 is itself. So negative 6 minus 12, negative 18, over 6 plus 12, 18. And again, 1 squared times 1 is 1, 1 to the power of 5 is 1. All of these 1's don't really affect our answer, and then negative 18 over 18 is going to be negative 1. And yep, that is correct. Okay, let's see some more practice problems. Okay, I think, all right, we have somewhat of an interesting next one. Oops. Okay, yeah, we have a bit of a unique next one. So we have x log base e of log base e of x minus x squared plus y squared is equal to 4, and dy dx at x equals 3. I mean, not x equals 3, x equals e is what we're going to do. This is an interesting one. It's kind of tricky. I think we can do it because we can do anything, but it's going to be a bit of a journey. So ln of x, because log base e is ln, I think they're just trying to trick us a little bit, minus x squared plus y squared equals 4. And then we need to find what the y value is when x equals e. So let's plug that in. We have e times ln of ln e okay, so let's hold on 1 second. I'm kind of confusing myself between the parentheses and the ln. So we have e ln e, not an extra parentheses out there, minus e squared plus y squared. Oh, they said that y is greater than 0. I didn't think that had any relevance, but then I saw, we're going to have to do a square root, so we need to make sure that y is greater than 0. Then this is equal to 4. Okay. E ln of ln e, so ln e is 1, because e to the power of 1 is e. So we have ln e, which is 1, and then ln of 1 is going to be 0. So this is negative, we just kind of sectioned it off. We have minus e squared plus y squared equals 4. We are trying to solve for y, so we bring that e squared to the other side. We have y squared equals 4 plus e squared. And we said that y is greater than 0, so y is equal to positive square root of 4 plus e squared. The idea that y is greater than 0 is important because this would have been plus or minus otherwise, and we would have had to do, extra calculations, and probably wouldn't have worked out. But we have y equals square root of 4 plus e squared. And then these derivatives are relatively normal. It's going to be a bit of a journey, but we can do it. So when we have to do derivative on both sides again. Yeah, I probably should bring y's on one side, x's on the other side, but we like to live on the edge, I guess. And this one's going to be both a product and a chain rule. So if we were to just look at chain rule, this is going to be our inside function, this is going to be our outside function, both of them are ln. So let's actually look at the outside thing that's happening, which is product rule. So derivative of the first times second plus first times derivative of the second, so this is going to be x prime plus, not plus just yet, but x prime times ln of ln x plus x times ln of ln x prime. I'm gonna do all this stuff later, but I have a limited space of screen, so I didn't want to write all of it out. And then from here, x prime is going to be 1, as we've said, because x to the power of 1 minus 1. If you bring that 1 out, it's going to be x. And anything to the power of 0 is 1 times ln of ln x plus this prime. Forgot to put that prime. This is what we are going to use chain rule for. So if this is our inside function, we are going to do x. That's still going to be on the outside. So it's going to be the derivative of the outside with respect to the input. So 1 over ln x. That would be like f prime g of x, if you'd like to think of it like that. Or, maybe even think of it as if this is like y of something, y of x, then y prime x prime, just dy dx. Kind of think of it like that, because we're doing implicit differentiation, but we have derivative of the outside, which is 1 over the inside, so 1 over ln x, plus derivative of the inside, which again is going to be 1 over x. The reason that this is 1 over ln x is, again, f prime g of x. So if this is g of x, then g of x doesn't actually change when you do f prime, and derivative of ln is u prime over u, or 1 over x. So from here, x's cancel, and then we're left with a nice and easy looking ln of ln x plus 1 over ln x. So we have ln x plus 1 over ln x minus, we said, derivative of the x squared. We bring that 2 out front. 2 minus 1 is 1. So 2x to the 2 minus 1 is going to be 2x. Derivative of y squared with respect to x is going to be derivative of y squared with respect to y times dy dx, or d dy y squared times dy dx, which, if we bring that 2 out front, 2 minus 1 is 1. 2 times y to the 2 minus 1 is going to be 2y times dy dx equals derivative of 4, which again is a constant, equals 0. All right, perfect. And now from here, we're simply going to plug in our y's and x's. Well, we could solve for dy dx. Actually, not we could. We are going to. So, inaccuracy on my part. Sorry. I'm getting excited, okay? I like to solve for dy dx, but let's plug this in. Or not plug. We're going to factor. We have dy dx, or 2y dy dx on this side. Then we will bring everything else to the other side. So we have 2x minus 1 over ln x minus ln x. And then we divide everything by 2y. 2y. Alright, great. And now we have x equals e, and y equals the square root of 4 minus e squared. Okay? And then from here, cancel out those two y's. We have dy dx is equal to all of that. And then we plug in x equals e. Again, for this one, ln e is, for this one, ln of e is going to be 1, and then ln of 1 is going to be 0. So all of that goes to 0. When you plug in e for this, you get ln of e is 1, so 1 over 1. And then 2 times e is still going to be 2e. So we have dy dx is equal to 2e minus 1 at the top. Well, minus 1 minus 0, but that's just minus 1. So over 4 times root of 4 minus e squared. There might be a way to simplify that, but oh, sorry, no, it's not 4 minus e squared, it's 4 plus e squared. And then from there, that's our answer. It was kind of hard, but I thought it combined most of what we were doing, and it it did have a lot more implicit differentiation than usual, which is nice. And then let's see. Okay. This one's gonna be hard. Not gonna lie to you, but I think we can do it. I think we can do it. Okay. So let's see how we want to do it. Our function is gonna be y equals x. Well, this is an implicit differentiation actually. Yeah, no, this is an implicit differentiation, so we're not gonna do it. It is a nice problem. I'll even show it to you because I like this problem, but I'm not gonna go through it all. Y equals. Actually, no. I do kind of want to do it. It's a fun one. I really do like it. But 1 over x squared n is what you have, and you're trying to find 1 plus x squared times the second derivative of y with respect to x, so d squared y over dx squared plus x dy dx. These kinds of problems look intimidating, but they're honestly not too bad. You just kind of need to know what you're doing. Fine, I'll do it. It's not implicit differentiation, but it is nice. So dy dx is going to be, since it's power of n, we can bring that n out to the front. We have n times x plus root 1 plus x squared to the power of n minus 1. That's our rule. And then since this is a function on the inside, we're going to have to not add, we're going to have to multiply by the derivative on the inside. So x plus square root of 1 plus x squared prime. Alright, and then from here, well, it's not really prime, it's d dx, but you know, we flip-flop between notation all the time. And then from here, this is another chain rule. We have this indoor function is 1 plus x squared, and our outdoor function is the square root of x. So 1 plus x squared, that derivative, bring that 2 out front. Derivative of 1 is 0, so derivative of x squared is going to be 2 out front, 2 minus 1, so 2x. And then square root of x is going to be x to the power of 1 half. Bring that 1 half out front, and then 1 half minus 1 is negative 1 half. So 1 half times the square root of x, or 1 over the square root of x. So I'm doing a lot of steps, but this isn't really implicit differentiation. I just thought it was a nice problem. Derivative of x, we said many times, 1 minus 1 is 0, so x to the power of 1 is going to be 0. I mean, x to the power of 0 is going to be 1. So we have 1 plus 1 half times the square root of 1 half times 1 over the square root of whatever's on the inside. So that's going to be 1 over 2 root 1 plus x squared, because this is, 1 plus x squared to the power of negative 1 half, times derivative of the inside, which we said was 2x. All right? And then this is equal to n, x plus root 1 plus x squared, n minus 1. All right, then these 2's cancel out, and let's write this last step a little bit neater. We are going to bring this 1, or we're going to bring this 1 into this function. So we have, well, this is going to be x because we multiplied this x over there. But we have dy dx is equal to n times x plus root 1 plus x squared, n minus 1, times x plus square root of 1 plus x squared, all over square root of 1 plus x squared. All right, great. Yeah, I just made this 1 into a term of square root of 1 plus x squared, and then I just, kept the x the same. Now we're gonna erase all that. And this is actually going to simplify rather nicely, so don't worry. Well, maybe this might use implicit differentiation. I don't know. We'll see. So, yeah, maybe I shouldn't have gone too quickly through this, but x plus square root of 1 plus x squared over 1 plus x squared. Square root of 1 plus x squared. We're just trying to simplify this to be in terms of, the same thing. And now from here, we are going to say that this is equal to, well, we're just going to bring this to the numerator. Since this is multiplication, we can have n times x plus root 1 plus x squared to the power of n minus 1 times x plus root 1 plus x squared all over square root of 1 plus x squared. All right, and again, this is x, all of this is the same thing to the power of 1. And these two have the same base. So when you multiply two exponents with the same base, you simply add those exponents, right? These are our original exponent rules. But yeah, x plus the square root of 1 plus x squared is the same thing as x plus the square root of 1 plus x squared to the power of 1. So since these are both the same base, we can actually add those exponents together. N minus 1 plus 1, that'll be n plus 0, so n. So in our numerator, we're going to have a n times x plus root 1 plus x squared, n, all over square root of 1 plus x squared. All right, and now from here, we are going to do a nice little substitution. I really like doing these kinds of problems because you have to think less about the actual math of what's happening and more about the logic of what's happening. We said that y is equal to all of this. So it's kind of like this is a loop. This is still y, right? We said that x plus square root of 1 plus x squared to the power of n is y. So we could just resubstitute that back in here, and we have ny all over 1 plus x squared. That's just cool, right? And from here, actually I think we are going to use some interesting, well, I'm not sure if this is actually implicit differentiation or not. I just know that this is pretty cool. And then this is, again, less about the actual math of what's happening and more about the logic. We said that dy dx is equal to ny square root of 1 plus x squared. So we can multiply this out to here, and we can say that ny is equal to square root of 1 plus x squared dy dx. That dy dx should be over there, but it doesn't matter. And from here, we can actually differentiate because we need to get d squared y over dx squared, right? And from here, we have another relatively normal derivative. So we are going to do, let's write this out up here. We have the 1 plus x squared, or the square root of 1 plus x squared, that dy dx. We are going to differentiate that again, so this is going to be d squared y over dx squared times 1 plus x squared. This is kind of like product rule. We have to do derivative of the front times derivative of the front, derivative of the first times derivative times the second, plus the first times derivative of the second. So this is going to be plus dy dx of this derivative. So 1 plus x squared, again, derivative of 1 is 0. Bring that 2 out front. We have 2x to the 2 minus 1, so this is going to be 0 plus 2x, which is 2x. And then square root of x, we said, is equal to x to the power of 1/2. Bring that out there. 1/2 minus 1 is 1/2, so we have 1/2 times 1 over x to the 1/2, or square root of x. So this is going to be dy dx times 2x, which we are going to multiply to our numerator, which is derivative of the inside. This is going to be chain rule once again. 1 plus x squared is our inside function, square root of x is our outside function. 2x over 2 root 1 plus x squared. Now these 2's cancel out, and this is again dy dx times all that is equal to ny. Wait, what am I doing? Oh, forgot. So we're doing dy dx of that is equal to ny. So when we differentiate this side, we have to do derivative of this and of that. So this is going to be n times dy dx. So yeah, from here, let's see. From here, we have the same dy dx is up here. So we're going to replug that in. We're going to have n squared times y over 1 plus x squared. And now we're simply going to divide every term by square root of 1 plus x squared. So, yep, that by 1 plus x squared, or by square root of 1 plus x squared, that by square root of 1 plus x squared, and then all of that by square root of 1 plus x squared. And then we get what our original goal was. Oh, wait. No, it's not divide. What am I? No, it's not divide. It's going to be multiplication. Again, we're trying to get to 1 plus x squared times the second derivative plus x dy dx. So this is going to be times, right? So we have, again, let's rewrite this. I'm sorry. I don't know. Maybe I'm just getting a bit tired, but d squared dy dx squared 1 plus x squared. We're going to multiply that term by square root of 1 plus x squared plus x over square root of 1 plus x squared. Again, we're going to cancel that out. Square root of 1 plus x squared dy dx, and then n squared y equals n squared y over 1 plus x squared times square root of 1 plus x squared, which means when you cancel all of these out, the only reason that we were allowed to do this isn't going to cancel. This is just going to take out the radical. The only reason that we were able to do this is because we multiplied by square root of 1 plus x squared on both sides. We have 1 plus x squared d squared y dx squared plus x dy dx is equal to n squared y, which is what we were originally asked for. Most of these problems have a similar type of like format. I know I didn't go super in-depth into it, didn't really explain my thought processes too well, but essentially what you're trying to do is you're trying to find the first derivative, and then you plug the original function back into the first derivative, and then use some implicit differentiation. We actually did use implicit differentiation when we said that square root of 1 plus x squared is equal to ny. It wasn't like a super big, dy dx. It wasn't like a very big implicit differentiation, but when we were doing this, we had to do dy of y times dy dx to get n dy dx. So yeah, it wasn't like a super crazy differentiation or anything, but we did have to use a touch of implicit differentiation to get that. All right, and now let's see some other problems. Okay. Okay. I think we have a good kind of flow going. So we're actually going to do that first problem that we were talking about earlier, like our second problem actually. I thought that, it was a bit of an extreme place to go for our second one, but I think we can handle it now because we've been doing some pretty crazy stuff. Again, we're going to have to do x to the power of y equals e to the power of x minus y, and we are trying to find dy dx. All right? And first off, like I said before, first thing that we're going to try and do is take out this e. Derivative of e to the power of u is relatively normal. It's just going to be u prime times e to the u again. But why make it more complicated than necessary? ln is a lot easier to differentiate. So we're going to do ln, which is the inverse function of e, so that we can cancel them out. Then we have ln of x to the power of y is equal to ln of x to y. Not x to y, of x minus y. Alright? And now we're going to do something kind of strange. You might seem, well, I'll change the format to log base e so that it's a little bit easier to see what we're going to do. So this is still e to the x minus y, and I'm going to use log base e notation, so it might be slightly easier to see the leaps in logic that we're about to make. Log base e of x to the power of y is equal to log base e to the x minus y. Alright, so this is going to be, we're going to be able to bring that y, or that x minus y out to the front. And then this log e, or log base e, x to the power of y, will become something a little bit interesting. With our natural logarithm, and with all of our logarithm properties, we can actually bring a number like this out here. Any exponent of a log can be a constant that is multiplied by that log, so this is going to be the same as y ln x is equal to, again, these logs cancel out, x minus y. And then from here, this is a relatively normal dy dx type situation. Well, we can actually bring this y to the other side, so we'd have y ln x minus y, or plus y, as it goes to the other side, so plus y. So if we factor out that y, it's going to be 1, is equal to x. And now from here, we're going to do some next product rule. Again, we're going to try and differentiate with respect to x on both sides. So d dx here, d dx here. Now from here, product rule, so derivative of the first, which is going to be d dy of y times dy dx times ln x plus 1 plus derivative of the second times the first. So derivative of this, derivative of a constant is 0, derivative of ln x is 1 over x, So this will be y times 1 over x, and that will be equal to derivative with respect to x of x to the power of 1, 1 minus 1, 0, so this will be 1. And now from here, nice and simple solving, derivative of y with respect to y is going to be 1 times dy dx, so dy dx of ln x plus 1 is equal to 1 minus y over x. I'm just bringing this y times 1 over x to that side, so it'll be 1 minus y over x. And then we just solve for dy dx. So we're going to have a 1 minus y over x over ln x plus 1 situation. And now from here, well, let's see. I feel like there might be some way to simplify this further. I don't think we need to, actually. Well, sure, let's do it. We said that y ln x is equal to x minus y. So we simply bring our y to the other side. We had y times ln x plus 1. So y ln x plus 1 equals x. So y over x is going to be equal to, let's divide both sides by ln x plus 1, is going to be 1 over ln x plus 1, right? We're just going to, manipulate our variables around, and we get 1 over ln x plus 1. And now we have 1 minus 1 over ln x plus 1 all over 1 plus ln x, or ln x plus 1, doesn't matter. And now we just, I'll show it out. So 1 is equal to ln x plus 1 over ln x plus 1. So we have ln x plus 1 minus 1 over ln x plus 1 all over ln x plus 1. So this denominator goes to that denominator because, fraction division. And then 1 minus 1 is 0, so we have ln x over ln x plus 1 squared. Okay? And the website that I'm using says that this is log, even though I'm pretty sure like some type of formatting error happened, because I wouldn't know how you can get log base 10 when you're working with E. But maybe if I did something wrong, somebody can comment down below. Let's see. We did that one. Okay. Yeah, let's try this one, actually. This one's interesting. Okay. Yeah, this one's gonna be hard, actually, but I think we could do it. So, this one's more of a word problem than an actual math problem, even though we are probably going to have to do a bunch of math. So, y squared is equal to ax squared plus bx plus c, the standard form of any quadratic, and y cubed d squared y dx squared, or the second derivative of y with respect to x, is four things. It's either a constant, a function of x, function of y, or a function of x and y. Those are the answers, exactly how they're given. I mean, I just use shorthand, but probably a better way of saying it. And I think you could kind of guess the answer. Um, yeah, I mean, to me, it seems relatively obvious that the answer is going to be f of x, but, you know, doesn't hurt to show our work. So let's do the derivative with respect to x on both sides. Oh, okay. Derivative with respect to x on both sides. So ddx of y squared is going to be derivative of y squared with respect to y. So bring that 2 out front. 2 minus 1 is 1. So derivative of y squared with respect to y times dy dx. So 2y dy dx is equal to ax squared. So a, b, c, these are all constants. They can't hurt you. So x squared, that derivative, we bring that 2 out front. 2 minus 1 is 1, so we have 2ax plus 1 minus 1 is 0. So you bring that 1 out front, you have x to the power of 0, which is 1. And then derivative of constant c is going to be 0. So this is what we have so far. And now we're going to get a little bit crazy. So this 2y dy dx can also be written, well, we're trying to get to d squared y and dx squared. So we're going to have to do this derivative over again, right? And when we do this derivative again, we're going to have derivative of the first times the second. So 2y, it's going to be d dx of 2y. So 2, it's just going to be 2 times d dx. Well, actually, no, getting a little bit ahead. Let's think. It's going to be kind of a weird looking thing. Okay. So, okay. I think we could do this. We're gonna have to do product rule. I know that much. It's hard to like think of what it would look like though. So okay. Okay. I think I got it actually. So derivative of the first. Sorry, I don't think I should cut this out. It does. I'm not a robot. I have to think about what I'm doing. So 2y times dy dx, we're going to do the derivative of the first, which in this case we're going to differentiate with respect to y. I mean with respect to x, so we are going to have 2 times dy dx, or times d dx actually, plus y, or not y, times y dy dx. Wait, is that correct? Oh, no, wait. Okay, I think I actually might have to look at this solution guide for this answer. I'm like 90% sure that it's f of x, but I don't, it's hard to prove why. Okay, wait 1 second. Yeah, okay, I'm on the right track, but they didn't explain what to do from here, so, okay. Yes, we do have 2 d dx times y dy dx. It's hard to explain how this like product rule works. It's more like we're just separating these ideas because 2 is a constant. It can be considered like, it's not really 2 is not affected by y in any way. So if you're doing dy dx of 2y, it can also be seen as 2 d dx times y dy dx. And from there, they also want to do the derivative of the other side. So d dx of this side, 2ax plus b. They're simply separating this into two functions. And no, wait, no, I think they just like wrote their work down slightly off. But yeah, 2y times dy dx, they're simply separating that y out so that 2d dx is the same as 2 times dy dx. 2 is not affected by y. So 2d dx times y dy dx, and then they're trying to do the derivative of this as well. So this derivative is going to be 2 dy dx squared. I'm actually not sure how this works. I mean, I'll show you the rest of their answer because I think everything past this point makes sense. But yeah, if somebody wants to, comment down below how this translates to that, that'd be great. I think I can see kind of where it's going. It's definitely, they're splitting that to dy dx into two separate functions so that it's easier to differentiate both of them, but I don't know why they would do that. Oh, wait. No, okay. Yeah, I got it, actually. So this is product rule. Derivative of the first times the second plus first times derivative of the second. So they're doing derivative of dx, or 2d dx. So this is going to be 2 dy dx squared. Again, this is going to be d dx of dy dx. When you multiply derivative of this times that, plus 2y times derivative of that. So d squared y over dx squared is equal to 2a. Then from here, you can solve, well, you could just kind of cancel out all these 2's. You're stuck with dy dx squared is equal to a minus y d squared y dx squared equals a minus, well, actually, we're not going to solve for dy dx squared. We're going to solve for y d squared y dx squared. So we're going to bring that minus a to this side. And then from here, it's kind of like a recursion type thing. Well, it kind of looks like recursion. So we're going to plug back our dy dx, which again we said was going to be equal to 2ax plus b. So yeah, if this is our dy dx, when we keep that 2, when we have that y still out there, this is going to be, 2ax plus b squared. Wait, what? Oh, no, signs are wrong. Okay. So yeah, wrong. This is going to be y d squared y dx squared is equal to a minus 2ax plus b squared. Just plug in this into that. And from there, we have we're going to multiply y squared to both sides. We get y cubed d squared y over dx squared is equal to y squared times a minus 2ax plus b squared. And then from here, since y was originally defined as, or y squared was originally defined as a function of x Don't know what happened there. Since y squared was originally defined as a function of x all the way up there, if y squared equals ax squared plus bx plus c, then ax squared plus bx plus c times all of this is still going to be a function of x. I think it's kind of obvious because you're differentiating with respect to x, and your input's always going to be an x. But yeah, that was weird. I didn't really like that problem. I thought I was gonna like it, but it wasn't interesting. I mean, it was interesting, but I didn't really get it too much. It took me quite a while, so if I don't think I can get it, then not in like an egotistic way. I just think that, if me trying to get it and I can't get it, then like most people, it may be like I'm missing something super obvious, but I think like it did say that this was supposed to be a hard problem, but yeah, let's go straight into the other one. Yeah, I just skipped that one. So yeah, I might need to cut that one out because not because like I'm embarrassed to not know what's going on, but because like I couldn't even satisfactorily come up with a good reason for why it wasn't working. But let's just go on to this next problem, which is also somewhat difficult, but it's definitely difficult in a more normal way. So we have e to the power of y times x plus 1 is equal to 1, then d squared y over dx squared is equal to something. All right? And, that's weird. So they're writing in terms of dy dx. Their answers aren't actually written in, correct format. Well, it's not incorrect format or anything, but they have their answers in terms of like 1 and then like dy dx and then like dy dx squared and then like y. Those are the answers. Oh, that's supposed to be a negative y up there. So yeah, this isn't, super math driven, but we are going to evaluate dy dx. So let's first solve for e to the power of y. We're going to divide both sides by x plus 1 just to isolate that y on one side and the x is on the other. So e to the power of y is equal to not negative, 1 over x plus 1. We're going to do ln to both sides, cancel out that e, ln here, ln there, ln everywhere. And now we have y equals, this isn't actually implicit differentiation. Maybe I should do this better. Okay, no, I'm not going to do it that way. I'll have like an actual dy dx, so I don't really like that. Let's try and use product rule for this one, even though that might make this more difficult, because this is an implicit differentiation video. So, we're going to do derivative of the first times the second plus first times derivative of the second. So, e to the power of y, derivative of that is going to be y prime times e to the power of y times x plus 1 times dy dx. So e to the power of y dy dx times x plus 1 plus derivative, or plus this first function, which is e to the power of y times derivative of the second, derivative of x plus 1, derivative of 1 is 0, derivative of x is going to be 1 minus 1, so x to the power of 0 is 1. So we have e to the power of y times 1, which is going to be e to the power of y, equals derivative of 1, which is going to be 0. And now from here, we subtract this term to the other side. We have dy dx is equal to negative e to the power of y over e to the power of y x plus 1. I kind of skipped some steps there, but essentially we're bringing this out there so it's easier to look at. We bring this e to the power of y to the other side, make that negative, and then divide by e to the power of y and x to the power of x plus 1, so that we can cancel these two out, and then we get negative 1 over x plus 1. There is a way to explicitly define that as a function of x, but why would you do that when you can implicitly differentiate it and make it maybe slightly more complicated than it needed to be? But, from here, we're just going to find the second derivative of negative 1 plus negative 1 over x plus 1. This one, there's no implicit differentiation to be found because there's no y's. So if dy dx is equal to negative 1 over x plus 1, then d squared y over dx squared is going to be, well, let's write this as negative x plus 1 to the power of negative 1. Bring that negative 1 out there. So negative 1 minus 1, that's going to be negative 2. And then this becomes a positive. Then we have to multiply it by the derivative of the inside because this is going to be chain rule. There's an inner function, negative 1 over x, and then there's an outer function, and that is, there's an inner function, x plus 1, and there's an outer function, negative 1 over x. So derivative of x plus 1, we said that was 1, so this is going to be positive x plus 1 to the negative 2 times 1. So you're going to have 1 over x plus 1 squared. And this is a tricky idea, but anything squared, so 3 squared is the same as negative 3 squared, if the negative 3 is in parentheses. Any negative when squared becomes positive, but that can also go kind of in the opposite way. We can write this 1 over x plus 1 squared as negative in parentheses 1 over x plus 1 squared, right? 1 squared up here is 1. X plus 1 down here squared is x plus 1 squared. So this negative, when squared, becomes a positive. So this still evaluates that, but we just want this negative to be here so that it looks like our dy dx. And so we can say that d squared y over dx squared, in this case, is going to be dy dx squared. That's going to be our answer for that one. Okay. Interesting. Okay, I think we could do this one, actually. This one doesn't seem too bad. Let's see. Okay, let's do it, actually. So, yep, that was more of a word problem. These last couple ones have been word problems, but this one's an actual calculus one. So, let's do it. We have 2x plus, not 2x, 2 to the power of x plus 2 to the power of y is equal to 2 to the power of x plus y. That is our function. Then dy dx is what we are trying to find. And for this one, we need to know that ln of, not ln, a to the power of u is equal to ln a. Well, actually for this one, it doesn't matter too much about u, so we're just going to write a to the power of x is ln a times a to the power of x. So that's, a relatively common derivative, but that's what we're going to be using for most of this. Now let's do this derivative. We're going to have d dx on both sides. Again, this is an operation, so anything we do to one side, we have to do to the other. So d dx of 2 to the power of x if a is equal to 2, that's just going to be ln 2 times 2 to the power of x. And then same thing with 2 to the power of y, except again, since y is not explicitly defined as a function of x, we're going to have to multiply it by dy dx. So we're going to have ln 2 times 2 to the power of y dy dx equals, and then for this, we're going to use some chain rule. We're going to do ln 2, that's ln of a, since a is still going to be 2, times 2 to the x plus y, and then since this is not an x or an y, it's a sum of two functions, we're going to have to do chain rule, so derivative of the inside and outside function. So 2 to the power of x is our outside function, x plus y is our inside function, and then derivative of x is going to be 1, derivative of y is going to be dy of y, which is 1 times dy dx, so 1 plus dy dx. Then from here, we simply solve for dy dx. Now we can cancel all of our ln2's because every single term in our expression has ln2. So we have 2x, or 2 to the power of x plus 2 to the power of y dy dx is equal to 2x plus y times 1 plus dy dx. And now we distribute. We have, well, let's bring this. I'm actually going to rewrite it just in this step. So 2x to the power of y times 1, it's just going to be 2 to the power of x plus y plus 2 to the power of x plus y dy dx. Isolate the dy dx's, so let's write it out like this. We have we're going to have 2 to the power of y minus 2 to the power of x plus y times dy dx is equal to 2 to the x plus y minus 2 to the power of x. Then again, we're going to divide that by this, 2 to the power of y, 2 to the power of x plus y, divided by 2 to the power of y minus 2 to the power of x plus y. Cancel, and then that will be our derivative. They want us to simplify it a little bit further. The answer is still the same, I'm pretty sure. Let's just simplify it and then see if that is one of our answers. And then from here, to simplify this, it's kind of an interesting idea. We know that x is common to both of these, so this is kind of like any addition of these exponents is going to be, those two exponents multiplied. If bases are the same, then exponents added means those two things were multiplied. So this will be dy dx is equal to 2x, or 2 to the power of x, times 2 to the power of y minus 1, all over, same idea down below, 2 to the power of y, 1 minus 2 to the power of x. Again, 2 to the power of x plus y, x plus y, bases are the same, so it'll be 2 to the power of y times 2 to the power of x. And then from here, by division of exponents, it will be subtraction, so this will be 2 to the power of x minus y, 2 to the power of y minus 1. Yep, this is an answer. 1 minus 2 to the power of x. And let's see if we are correct. Yep. Okay, yeah, we're correct. And let's see. Okay. This is somewhat similar to another problem that we did, that kind of weird one that I didn't really know what I was doing. But this one is a lot more straightforward. Not necessarily easier, but it is a lot more straightforward. So we have x is equal to y squared of y, or square root of 1 minus y squared, and then dy dx is something. So they already did this nicely. They separated the y's for us, but we're going to put it on the left-hand side. Y minus 1 minus y squared is equal to x, d dx of both sides. So again, this is going to be product rule and chain rule. Inside function, square root of 1 minus y squared. Outside function, square root of x. So it's not really square root of x, but square rooters are outside. 1 minus y squareds are inside. So 1 minus y squared, let's do it out here. I'm not going to use dy dx just yet, but we are going to have to think in terms of dy dx. So bring that 2 out there. We have 2y, and then derivative of 1 is 0, so we're left with negative 2y. And then square root of y, let's say. This is y to the power of 1/2. And as we've said, this will be 1/2 y to the negative 1/2. All right. And then from here, let's write it down. We are going to have I'm actually going to use prime notation just to make this a little bit easier to look at. Y prime times 1 minus x squared plus y times, I'm actually going to drop y prime notation immediately because we just evaluated all of the necessary derivatives. That will be negative 2y all over 2 root 1 minus y squared. And I put an x there because I don't know why. Get it? I don't know why. Okay, it's getting a little bit long as a video, but okay. So we have y times negative 2y over 2 square root of 1 minus y squared. Again, we had negative 2y from the inside derivative, and then 1 over 2 times 1 over 2 times square root of 1 minus y squared is the derivative of a square root, and then this is going to be equal to 1. And I forgot, this is also with dy dx. And that's all going to be equal to 1. Then from here, derivative of y is going to be d dy of y, which is 1, times dy dx. So we're going to be left with square root of 1 minus x squared dy dx minus, wait. Okay. This didn't have any answers, but I'm not sure. I looked at the solution just to make sure I didn't embarrass myself or anything, and kind of don't think it's correct. We'll see. We'll see. Maybe I'm doing something wrong. So I'll look at their work. Okay. I don't know. I think we're okay, actually. Yeah, I don't think this solution's correct. It says that this 2 doesn't exist. But again, when we do square root of 1 minus y squared, we have to do square root of the inside, so negative 2y over 1/2 times y to the 1/2, or in this case, 1 minus y squared to the 1/2. So these two should cancel out, but this answer is not looking right. So yeah, I'm actually gonna make something that I'm going to do something I don't usually do and assume that I'm right and this technology is incorrect. So, yeah. um, if I'm making some type of very stupid calculation error, somebody please correct me down below so I don't make more of a fool of myself than I already am doing. But from here, let's just, do it normally. We have square root of 1 minus x squared minus, these two cancel out, and then we have minus y squared over square root of 1 minus y squared times dy dx is equal to 1. And now we simply solve for dy dx. I don't know why I keep putting x squared. It's not x, it's y. But square root of 1 minus y squared. And then from here, dy dx. You can put these two together and bring that dy dx out there. Then divide everything on that side. So we have 1 over square root of 1 minus y squared minus y squared over square root of 1 minus y squared. And, yeah, let's simplify this. It's not too hard, actually. I'm overreacting. I think it's fine, honestly. So we're gonna multiply both the numerator and the denominator by square root of 1 minus y squared so that we can rationalize whatever radicals we have underneath. So we have square root of 1 minus y squared in the numerator now times 1 minus... Wait, what? Let's think. Actually, no, I'm good. So this will be times 1 minus y squared minus y squared. So we're going to be left with square root of 1 minus y squared over 1 minus 2y squared. Again, if I made some type of mistake, please comment down below. The answer says that it's 1 minus 3y squared, but I'm pretty sure we do still have that 2 in the numerator, so those two do cancel out. But yes, our dy dx is going to be 1 minus y squared, or square root of 1 minus y squared over 1 minus 2y squared. And now, let's see. We've done quite a few of these practice problems. I'm not sure if I can find another good one. Let's find something. Okay. Yeah, some of these are pretty good. Let's do some nice and easy ones. Y equals x tan y. We're trying to find dy dx. So we can't really isolate the dy dx's, or, well, we could, but let's do it. I'm very indecisive at this point, but we have y equals x tan y, so we can simply bring that y to the other side. X tan y minus y equals 0. We're going to do derivative with respect to x on both sides, and we get product rule. That's what we have to do. These are two separate functions, so ddx of x, which is going to be 1, times ddx of tan y, or not ddx of tan y, times tan y, plus x times ddx of tan y, which is going to be 1 over cosine squared. We can just do that real quick. Tan x is equal to sine x over cosine x. So this will be a nice quotient rule. Derivative of the top, which is sine x prime cosine x, minus sine x times cosine x prime, all over cosine x squared. So sine x derivative is cosine x, cosine x derivative is negative sine x, so that becomes positive. So we're going to be left with sine squared x plus cosine squared x, all over cosine squared x is equal to 1 over cosine squared x. So this is, just something you should probably remember, but derivative of tan is going to be 1 over cosine squared, or secant squared, as you might have seen it before. But this will be x times, oh, wait, I'm not sure if this is asking for secant squared or not. Oh, they want me to simplify it. Okay, I'm actually going to use secant squared for this one, though. So this will be x times secant squared y times dy dx. Again, this is going to be derivative with respect to x of tan y. So we're going to have to do dy of tan y times dy dx. And then from there, derivative of negative y is going to be negative 1 times dy dx. So dy of y times dy dx, so negative dy dx. And then from here, we simply solve for 0. Wait, let me see. No, we're good. Okay. Equals 0. Now we'll bring every, non dy dx onto that side. So we have x dy dx of dy dx of 1, not 1, of x secant squared y minus 1 is equal to negative tan y. And since I don't want to have a negative, I'm just going to flip these two. So the x secant squared y minus 1 is the same as negative 1 minus x secant squared y. So I'm simply going to write dy dx when I divide both sides by x secant squared y minus 1. I'm going to rewrite this as dy dx is equal to tangent y all over 1 minus x secant squared x secant squared y. And yeah, from here, we're going to have to simplify this further because none of these answers have secant anywhere close to them. So yeah, let's try using a well, we have secant squared, so one of the trigonometric identities that you learn from sine squared plus cosine squared is secant squared minus 1. And I don't really like to memorize them. I like to just kind of think about them. So if I know that sine squared x plus cosine squared x is equal to 1, I can simply divide every single term by cosine squared or by sine squared, depending on what thing I need to remember. Cosine squared x, cosine squared x. And then you get to sine over cosine is tangent, so tangent squared x plus cosine over cosine 1 equals 1 over cosine, so secant squared. And this is how I tend to remember these. I'm not the biggest fan of using the, just brute force memorization. I just kind of like to think about how I would get to that idea from my head. But yeah, it doesn't matter too much. So, tangent y, if we said that y is equal to x tan y, then we can divide both sides by x to get tan y is equal to y over x. That means that tan squared y, or this squared, has to be equal to this squared. So this will be y squared over x squared. And again, we said that secant squared minus 1 is equal to tan squared. So secant squared in this case is going to be equal to, well, I don't know why I wrote it like that. We already said that tangent plus 1 equals secant squared, so this will be 1 plus x squared over y squared, if this is tangent squared. Alright, and then from here, we simply need to plug this back into our dy dx. Normally I wouldn't bother to do any of this, but the answers that are given do not have secant in them, so you have to do some manipulation. So we have tangent y over 1 minus x secant, or not secant, because we just changed that to 1 plus, it's not x squared over y squared, it's y over x. So 1 plus y squared over x squared. So we have 1 plus y squared over x squared down there. And then from here, you simply have to distribute. So we get tangent y over 1 minus x squared plus y squared over x squared. I'm just bringing that 1 into the x squared, so it might be a little bit easier to simplify. And then from here, I just cancel those x's out, have an x down here, and then, we have, actually, I don't think the final answer is going to have tan in it either, because we're going to do another interesting trick. So we have we have regular tan y up here, and then we have 1 minus x squared plus y squared over x down here, and then we can bring an x in there. We have x minus x squared plus y squared over x is in the denominator, which means that we can actually bring this x all the way up to the numerator when we flip these fractions. So we're going to be left in the end, after all this somewhat unnecessary manipulation, we're going to have x tan y over x minus x squared minus y squared. And then remember, we said that y is equal to x tan y. So that means that our numerator is also going to be y. So yeah, I guess that is perhaps slightly easier to plug values into for getting, derivatives, but honestly, most of this was unnecessary. But yeah, that's a nice dy dx. And I think, let's see how long I've been recording. Okay, I've been recording for quite a bit. So yeah, that was some 2 to 3 hours of derivatives. I hope, I pray, I hope that anybody who's managed to suffer all the way through this point has some understanding of implicit differentiation. Just to sum everything up, implicit differentiation is just a unique use of chain rule. When you are given a relation that is not a function, and you are trying to define, it's almost always going to be x and y, but as you've seen today, we have had some, other variables, but most of the time it's just a constant, it's not actual variables. But whenever you have these types of problems, what you're going to have to do is use chain rule. You're going to have to describe y as a function of x, and then find the derivative of y with respect to y, and then multiply that with the derivative of y with respect to x. I'm hoping that the translations between chain rule and implicit differentiation are pretty apparent. I know it's pretty abstract. That's probably the best way to describe it. When I first saw implicit differentiation, it took me a long, long time to fully understand even what I was doing. I was just kind of, I did derivative of y, so I have to do dy dx because that's what you're supposed to do. I didn't really understand what I was doing, but yeah, now I know. Like, Implicit differentiation is just a different use of the chain rule to find a derivative of a function that is not a function of x, or that is a function of x, but not explicitly defined as a function of x, so that you can solve for dy dx. Um, that wasn't like the best sum up or anything, but I hope that these examples have shown you that implicit differentiation is difficult. It's not, inherently easy or anything, but it's just an extension of normal differentiation. And at a certain point, it'll just come to you naturally. So, yeah, I hope you learned something. Wait, what's my outro? Okay. Um, Shoot. I need to watch back one of my videos. It's been a while since I've started recording again, but thank you for watching. If you like this video, please comment down below. If you did not like this video, constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, then you can, I don't know, suplex something. And for today, my album recommendation, I don't know what I've been listening to. Haven't really had the time to listen to a lot of music, but I mean, I've already recommended it, but Blackbird by Donald Byrd, listen to that way too much recently. Been getting back into Liam the Havas. Oh, I do remember. I've been listening to a lot of Bubba by K Tronada. Not sure if I'm saying that right. Bubba. I think it's stylized in all caps, but it doesn't matter. K Tronada. It's this weird intersection between house and like sample-based hip hop and jazz, and it's crazy. It's just so unique, you know? It's like a breath of fresh air. I mean, I'm not a big house like genre fan. I don't have any use for house in like my daily life. Um, I'm not bumping EDM on the bus, but you know, I appreciate it as a genre, and Bubba's definitely become one of the most interesting albums that I've listened to this year. Like, every single song, they do have the same, like, production. They have the same quality and same ideas, but they aren't exactly the same. That's one of the things that I dislike about house as a genre. It's very repetitive. Most songs sound exactly the same, but K Tronada is able to bring in inspiration from several different fields of music, almost always like black music and African American like inspirations that he's had in African music, but it's just it's fascinating. It's a very interesting breath of fresh air, and like you know, most of house is dominated by uh, a very specific group of people, and K Tronada is definitely he brings something fresh to this somewhat stale genre. So yeah, I encourage you to listen to it. Um, Maybe yeah, I think if you listen to the first track and you like it, you'll probably like the rest of it. Because, again, it's not repetitive or anything, but it does have the same ideas communicated throughout and the same kind of, like, feel to every track. But, well, actually, no, that's an inaccurate thing. I feel like most of these tracks are relatively distinct. Like, you can recognize each track, but each has the same goal to make you feel the same thing. So, yeah, if you do listen to this album, please comment down below what you thought of it. And, yeah, see you next time. I need to see what I've been saying. But, bye.